The software industry is currently optimized for a singular promise: give an artificial intelligence total autonomy, step back, and watch it generate endless code until the project collapses under its own weight. We measure these tools by the size of their context windows and the speed of their generation. But equating an agent's autonomy with developer productivity often leads to cognitive atrophy and a slow decay of the underlying system architecture. This happens because large language models are probabilistic copilots. They are designed to predict the next most likely token, not to act as deterministic engineering engines. While the friction of writing syntax has been removed, so has the productive struggle. This is the effort required to learn how a complex system actually holds together. To transform raw AI into a serious educational environment, we must move away from passive delegation. The goal is to implement structural governance. This environment relies on three specific pillars: progress memory, design-first planning, and sandboxed execution. Prioritizing rigid structure over generation speed ensures the human remains responsible for the logic. It is a framework designed to build engineering discipline rather than just increasing the volume of code. Passive chat histories inevitably degrade structural context. As a project grows, the useful information is buried under iterations, temporary bug fixes, and abandoned ideas. This is the vacuum hypothesis. The time saved on generating syntax is eventually lost to architectural archaeology. The developer has to hunt through messy chat logs just to understand the current state of the application. This gap creates a hallucination of continuity. As shown, the project splits. The solid path is actual code. The fading path is the AI's outdated mental model. It might propose a solution based on a folder deleted hours ago, infecting your current codebase. For a student, this turns learning into a search for context. They spend more energy checking the machine's assumptions than they do understanding the software logic. The solution is to move from a passive chat history to what we call progress memory. We extract human decisions into deterministic configuration files, like agents.md. These dissolve the chaotic timeline, reorganizing the project into a tree. This file hierarchy acts as a strict interface contract, forcing all newly generated code to stay within established parameters. Shifting from a passive chat to an active archive changes the student's role. They are no longer just reacting to generated text. They are acting as a system architect. Securing the archive is only half the battle. We must also address the exact moment before code is executed, the initial prompt. Allowing an AI to immediately modify the working tree bypasses architectural verification, the stage where a developer conceptualizes how a change affects the wider system. We enforce a planning mode as a mandatory checkpoint. Instead of a monolithic code block crashing into the system, work is broken into organized cubes that pass the plans.md date. Each plan defines the scope, constraints, target files, and a rollback procedure. This discipline mirrors the research from Dora, particularly the importance of batch size. Reducing the batch size of code modifications through planning directly correlates with higher deployment stability and easier debugging. Pedagogically, this is vital. Refusing a flawed AI plan teaches defect prevention at the conceptual level, which is more formational than just correcting syntax line by line. The modern productive struggle is no longer about typing characters. It is about anticipating side effects and defining test vectors to prove a solution holds. By slowing down the AI during the planning phase, we ensure that human intent remains in control of the system's actions. Once the plan is set, the system enters the execution phase. This is where code interacts with the external world and third-party services. Many educational workflows currently teach students to paste API keys and session cookies directly into prompts. This turns the student into a token manager rather than a secure developer. This creates a systemic vulnerability. An AI node blindly accepts an unsanitized payload from an external API, injecting it into a local database. This is OWASP API 10. Learners implicitly trust third-party data handled by AI, bypassing the sanitization required to keep systems clean. To fix this, we implement the Model Context Protocol combined with OS-level sandboxing. This limits the AI's write access to the project root and blocks unaudited network calls. We also utilize an isolated AI-controlled browser profile. This separates the student's personal data and the host OS from the experimental workspace. By using modern standards like OAuth 2.1, we abstract secret handling away from the student's prompt entirely. The student focuses on the integration logic, not the manipulation of raw keys. Visual inspection through these isolated browsers allows students to see the DOM and network requests in real time, converting abstract concepts into tangible engineering phenomena. Decoupling execution from secret handling transforms the IDE into a zero-trust laboratory, teaching the student to govern systems rather than just manipulate them. This blueprint for an AI-native development environment is divided into 3 distinct chambers: the active archive, the planning gate, and sandboxed execution. Together, these 3 pillars ensure that the AI speed never outpaces the developer's comprehension. Human in the loop is often sold as a simple binary approval button. This is a dangerous misconception. If forced to click approve on hundreds of microactions, a student succumbs to alert fatigue. They stop reading and start clicking, which cancels out the pedagogical benefit. True human in the loop is a discipline of strategic interruption. The human node acts as a gatekeeper. At the planning gate, the human injects constraints before generation begins. At the execution gate, they validate output before it is committed to the archive. The modern developer's core capability is no longer syntax generation. It is the ability to design robust evaluations that prove a system's behavior is correct. Mastery in the AI era is measured by the sophistication of the active archive, the rigor of the planning, and the capacity to govern automated systems with technical responsibility.